submerged body. First, we look at flat plate, that is submerged. Then we went on to look at curved surface, which is the hull, of a ship that is submerged in water. Because it's affected by hydrostatic forces. And these hydrostatic forces will vary in magnitude as you go down. Okay, so you got an integration sign. And then we look at how we can therefore find the resultant force. Okay, and also the location of that resultant force. Now, just one or two things I'd like to correct. Because my eyesight is not so fantastic with the progressive lens. Okay, you can see this, eh? You see? I think that is the best. This is the best. Not too many manual. Everything is there. Very limited space. Okay, so we were looking at this is for the flat plate. And just go back. This one. Okay. Okay, the depth. Okay, this is the depth. Right. We were working all the way down to here. This is the resultant force acting on the depth. Okay, where does it act? It acts as a point, location of the resultant force. In order to know where it acts, you first must look at where the components act. Okay, so the component location of the y component that's coming down, the y component from D, which we call it xd. Okay, xd is given by this expression. Do a correction here. This should be xd times the area of the triangle. Area of the, I put a triangle sign there. Here also triangle. Okay. Area of triangle ABC on that question. Okay, so xb is therefore 0.33 meter from D. 0.33 meter from D. Or you can say, add on, or it is how many meters from A? How many meters from A? From C, sorry, from C. It would be 4.67 meters from C. Okay? So, depending on the question, if the question says find xb from D, then you answer with 0.33. If you say find xb from C, then it will be 0.67. Alright, just a slight simple mathematics. Okay, now if you go back to the curved surface example, the curved surface example on the, to find again the location of the horizontal and vertical forces. I hope this is clear. Why? Because the question asks you for the location of the FR component. Okay, let me just the FR component. This is okay. Now, if you look at the computer slide, the computer screen, you see that FYX 0.33 meter from E or 0.67 meter from C. And we also found that for this question, the FX, where it is. Okay? So, since you know where FYX to be this point, which is 0.33 meter from this vertical line. So therefore, the location of the resultant force must also be at this point. Okay? Resultant of the location resultant force must also be at this point here. Alright? And of course, we have, you can go about, the magnitude is 2462. 2462. Okay? So finding where Fy is, we'll therefore be able to locate this point. So Fy is the vertical component of Fr, and Fx is the horizontal component of Fr. Okay? So Fr at this point, which is again 0.33 meters from this vertical line. Alright? Now, back to the earlier, back to earlier example before the gap is this example here. And we have to find the location of the horizontal and vertical forces from points E and D. And I put them from points E and D because one of you asked me, so why do you find Fy from D and not from C? Okay? Why do you find location Fy with respect to D and not from C? The answer to this is, anybody can answer? Why? Anybody can answer? Same, let's say. Same meaning for answer is the same. I mean, in terms of practicality. Okay, why? Because the question says find the location of the horizontal and vertical forces. Full stop, right? Full stop. So, okay, I want to make it clear. Yeah, guide you. Okay, from points E and D respectively. Okay. So Fy from E, okay, and Fx from E. Okay, so you can add that the last few words to add on to it. So why not from C, but from D? Anybody? Where's Ashit? Ashit, where is he? Oh, I give attendance sheet, Ashit not here. Huh? Have you one? There you are, attendance sheet. Please look side for your friends. I see who attendance, but I don't think I see who all of who are 70 plus or around there. Oh, less than who, so no, not who, I count already. Every time who attendance cannot be, right? Okay, so Ashit not here. Anybody can answer the question? About doing catch what? Oh, Ashit, very shy. Yes, Ashit. C is an imaginary point. Very good. Very good answer. C, you see, okay, on paper, you can always draw broken lines and you can always locate any points you like on paper. But if this is applied in practice, and you tell the shipbuilder, okay, I need to explain to him, and you say, okay, Fy is actually a certain distance from point C. From point C. Then the shipbuilder uses point C, point C is somewhere in water, in the water. How to find that reference point? Someone is at the intersection of two imaginary lines. At the intersection of two imaginary lines. So how do you imagine a line? Say, this is the point. So therefore, for practical application, we try to take reference from some realistic point, realistic reference, rather than some imaginary, hard to locate reference. Okay? Alright. So anyway, just guys, I've added from points E and B respectively. Just to be clear. Okay, good. Alright. So today we will continue from where we left off, and that is to look at flow visualization using streamlines and half-lines. Streamlines and half-lines. Okay. So the first part of today we'll be going to lecture, and then the last 45 minutes or so we'll look at some tutorial questions. Okay? Alright. Okay, flow visualization using streamlines and half-lines. So, one thing for fluid mechanics is that, because fluid, we're not looking at a microscopic view, because a fluid particle consists of molecules. Molecules consist of atoms. So we're not looking at a microscopic level. We're looking at a macro. If you look at the microscopic level, it's not the much, it's just very complicated. It's very complicated. And in fact, even if you look at the macroscopic level, it's very complicated because fluid is a continuum. So how do you come up with theory and to analyze flow of a continuous continuous method. So one thing fortunate about fluid mechanics is open to visualization. So there are many theories in fluid mechanics that are difficult to solve. Later on you will see next week or so, Navier-Stokes equation. Navier-Stokes equation is a very complicated equation in 3 dimensions. Okay? And it involves many variables. So it's not completely solved for even practical situation. Even CFD, so people use CFD, computational fluid dynamics, simulation. That can only do for simple practical cases using the Navier-Stokes equation. So theory is very complicated, and with this course we'll be covering the fundamentals. Yes. Fortunately, fluid is open to flow visualization. So many things which physicists, engineers cannot understand or cannot solve, they go to do flow visualization. For example, you inject a dye in the fluid, like that's what Reynolds did, and able to say, okay, when at a certain flow rate, the flow becomes rather transitional. Sometimes laminar flow, sometimes turbulent flow, because it's a dye. So you can see as the dye follows the flow of the water in the pipe. And when you increase the valves even more, the flow goes faster and becomes very turbulent. And so fortunately, fluid mechanics is open to flow visualization, and physicists and engineers are able to use experimental observation to complement their theoretical analysis. Okay? So the very basic thing on flow visualization is that first is half-line. Half-line. So what is a half-line? Basically, from layman's point of view, is your half-line. If you go from point A to point B to point C, you fall down. Then point D, that's your path. Okay? So imagine if you are a fluid particle, that's flowing this way, that's the path line of the fluid particle. It is your the locus of your location at different instant in time. So look at that. You see, the fluid particle, the blue color one, you have T0 is the starting time. Okay, this is particle. At time T1, it is there. The fluid particle has moved. So at time T2, it has moved to there. At T3, it has moved to there. At time T4, it moved to there. And then for this green fluid particle, same. At time T1, it has moved there. It's slightly different from the blue particle. And so on and so forth. So on and so forth. So they vary. Yeah, so you see that actually their speed is different. Okay, or their velocity is different. Okay? So, fluid mechanicians, they want to define half-life as a very fundamental definition in fluid mechanics. And we're just considering two-dimensional, x and y plane, and u component and the v component of the velocity. Okay? So, x and y plane and the u component direction and the v component direction of the velocity field. So we have, for a two-dimensional flow field, we have the following relation. That u is the horizontal component of the fluid velocity or the fluid particle. Okay? And v is the vertical component or the y component of the fluid particle. Right? So u is the x dt and v is the y dt. So this is basic simple mathematics. Okay? Now, then with the definition and mathematical expression for half-line, then we have also streamline. Streamline. So what are streamlines? Streamlines actually tangents drawn to the velocity vector. This fluid has velocity. So velocity is a vector because of magnitude and direction. So streamlines are drawn to the vector velocity vector at every point in the fluid domain. Okay? And so if you see all these red arrows there, okay? These are streamlines. Okay? These are streamlines. Right? So again, in the two-dimensional flow field, we have the following relation for streamlines involving the horizontal component of the velocity and the vertical component of the velocity. It's given by this relation. So this is a streamline relation. Okay? That was a half-line. This is a half-line relation. This is a streamline relation. dy dx is equals to d over u. Okay? So half-line relation and streamline relation. Okay? I call it equation of streamlines. A relation is same as equation. Okay. So to understand this, it's good that we look at a word example involving spray coating. So you have here the nozzle spraying out titanium powder onto a surface to coat it. Okay, to coating a surface with titanium substance. This to basically to harden the surface. So we have here the velocity profile of a two-dimensional fluid flow field. Fluid flow field, FIELD, is given by this v. So v with arrow means it's a vector. It's a velocity. The velocity v is a vector. Just an arrow on top. Is equal to axi minus yji. Okay. What is this I? I hat. In your applicable math, you come across I hat, right? What is I? And what is j? What is I hat and j hat? They are unit vectors. They are unit vectors. Okay, in the x and y direction. You learn in applicable math. They are unit vectors. So xi, it means the u component has a displacement x in the I direction. Okay? And the v component has a displacement is minus y. Okay? In the j direction. Where a is a constant given as 0.3. Consider the flow is incompressible. Okay, very important. We look at incompressible. So we also cover to a certain extent compressible flow later on. Okay, but basic only of compressible flow. Consider the flow is incompressible. It is steady. Okay, no variation with respect to time, and is non-Newtonian. Okay, so we have to worry about that non-Newtonian. Now, one is obtain an equation for the streamlines. Okay, obtain equation for the streamlines. So obtain equation for the streamlines. So how do we go about doing that? So we have
Newton means.
So obtain equation for a streamline. Okay, so how do we get started? How do we get started? So first, we have this velocity vector is 1. This velocity vector v is equal to a xi hat minus y j hat. This is given. Okay? Is it there? And we know so from here we can see that here actually the horizontal component of the velocity vector or the velocity vector u is actually ax. Okay, so a times x is actually your u, and a times minus y is actually your v. So v is equal to minus a y, deduction from above. Okay. So in this case here, from earlier slide, slide 66, okay, from the equation of the streamline, we have dy dx is equal to d over u. Okay, that's the equation of the streamline, slide 56. Okay. So we just multiply the right side of the equation by a over a. We are not changing the equation at all. So dy dx is equal to just substitute there first before we go too far. So d over u, what's d over u? D over u is substitute into here, will give you minus ay over ax. Okay, minus ay over ax. So a can cancel, So dy dx is equal to minus y over x. Okay, minus y over x. So rearranging, you have dx over x equals to minus dy over y. Just by rearranging. Alright, so if you have a differential equation, so what we're going to do is find the expression for streamline of this particular flow, the streamline of the flow. So in this case here, we need to integrate. So if we integrate the x over x, the left hand side, you must also integrate dy over y on the right hand side. Now, so from applicable mathematics, if you integrate 1 over x, dx, what do you get? Log x. Good. And similarly on the right hand side, you get minus log y, and don't forget your constant. Okay, let's call it log c. Here is a constant anyway. So you can just rearrange this, and you have log x plus log y equals to log c. So this is equal to log xy. Log x plus log y, the addition of two logarithm terms is equal to logarithm times the logarithm term of the multiplication of the two terms. So it's equal to log c. Just rearranging. And therefore xy is equal to c. Okay? So this is the equation of the straight line of the jet flow. Okay? This is the equation of the straight line for the jet flow. xy equals c. So there's no time there. Time doesn't go in there. Right? xy equals c. So how do we interpret this? Okay, xy equals c. So how do you actually able to sketch this? Okay, just sketch. So before we sketch, we will give some numbers. So this will give different streamlines with different values of c. So for example, you have a table here. Example. You have your c here, you have your x here, you have your y here. Okay? So you have to fix some of it. Let's say x 0.1, x 0.1, x 0.1. Just fix it. And now, if you can refer to the next slide, 111, xy is equal to c, and c can vary. So, see the jet flow, see the flow there? See that? Okay, never mind, I'll just do a sketch afterwards. So, let's say, give it some value. With your y equal to, let's say, 25 and 50. This is 100. Okay? So from that simple equation, if you set values of x and y there, your c, this will give rise to a family of straight lines. In this case, c will be 0.1 times 25, will be 2.5. Okay, this will be 5, and this will be 10, and so on and so forth. Okay. Now, question says plot. We just sketch. Sketch some streamlines. So we see at different values. It gives you different streamlines. Okay, on the xy plane. So, in other words, if you let's try to sketch, let's sketch. Okay, if you have, for example, this is your x-axis, and this is your y-axis, right? And you have values like, for example, this is 50, y is 50, y is 100, y is 150, and so on and so forth. Okay, and here this x is 0.1, 0.2, 0.3, and so on and so forth. Okay, will it give rise to a series of streamlines? So, I mean, in fact, I'm just doing just 3 points. Okay, so if a proper plot using a computer, you can do a lot of lines. So in other words, basically, when it's 0.1, x is 0.1, y is 25. So somewhere there, this one belongs to a streamline. Okay. So when x is 0.1 and y is 50, this one give rise to another streamline. Here, right? Okay, another streamline here. And when x is 0.1, y is 100, c will be 100. Okay, so this one. So this represents points on different families of curve. I'm just doing 3 points only because I can't perfectly do the whole plot here. So, okay, let's do the color. So you get straight lines like that. Okay, if you were to do proper plotting, you get straight lines like that. You get another straight line, like this. You get another straight line. And similarly on the other side also. Okay? Similarly on the other side. Alright? And so on so. This just to demonstrate the idea. So sketch some streamlines on the flow on the XY plane, in order to visualize the flow field. Right? So you can therefore say that this is for C, you put black color, blue color. This is for C equal to 10. This is for C equal to 5, and this streamline C equal to 2.5. So we have a family of streamlines, okay, represented by a family of curves on the XY plane. So you can see this is up to a sketch. Then 3 is x and y. Okay? So you will see that here, x and y can be any point and any streamline. Okay? So now the question is, if x and y is equals 0.2 and 0.8, 0.2 and 0.8, so somewhere on the very bottom streamline, 0.2 and 0.8, very, very low, very close to the x-axis, this point. And this was the initial position of a fluid particle. What will be the new position of this fluid particle at time t is equal to 6 seconds? So you start from a very low point somewhere there where x is 0.2 and y is 0.8, somewhere there. Okay? At time t equals 0. So following this, okay, where will this particle be at time t is equal to 6 seconds? At time t equals 6 seconds, where would it be? So in other words, you have a strip line there. Okay, this one. Very, very close now to the x-axis. You're almost touching the x-axis. And go all the way. So at time t equals 0, we choose a fluid particle. It's a 0.2 and 0.8. 0.2 and 0.8. So it's somewhere here. Somewhere there. Time t equals 0. At time t equals 6 seconds, where? At time t equals to 6 seconds. So, what I'm saying, it didn't necessarily go down. It could also, because of the splash, right, it could also do this. Okay? Because if you spray something, you spray then just spread out. So when it hits, it just go this way, just go like that. So it does sometimes go up. Okay? Because of it. So it does. So what is the position of the particle at time t is equals to 6 seconds? Okay, that's 3, yeah? 3. Now, so 3. We have for a path line, yeah? For a path line, what we got now, equation for a path line, the horizontal component of the velocity vector is ax. Okay? The vertical component of the velocity vector is minus a1. That's how we have got. Okay? Now, so we also have u is equals to x dx dt. We know u is dx dt, and d is actually dy dt. Okay, from our earlier slides. So let's first take the x component velocity. Then let's take the u first. Okay. First, we take the x component velocity. First, we consider the u first. U is dx dt. Okay. So we knew from above, u is ax. So i.e. ax is equals to dx dt. Okay. So we can rearrange that, and then later on we can integrate. So we have rearranging the x dt is equals to a dt. That's by rearranging. Okay. Because what we're trying to arrive at is a simple expression relating x and t. X and t. Now we have dx and dt. So we have to integrate. Okay. So to integrate, we have therefore integral of dx over x, dx over x. Sometimes dx over x equals to a dt. Yeah? So you integrate dx over x on the left hand side, you must also integrate the right hand side. Right? So that the whole thing remains unchanged. So if you do that, integrate 1 over x, you will therefore get, because our applicable max is log x. Okay? And on the right hand side, integrate a constant with respect to time, you get a t. Plus a constant, let's put c. Okay? Now, so what do we have to do next now? We define c, what c is. Okay? This constant of integration. So we can use some values given to us. We know that at time t equals to 0.2, t equals 0, x is 0.2. So at time t equal to 0, our x is given as 0.2. So substituting, you have log of x is 0.2 is equals to t equal to 0, 0 times a is 0 plus c. Okay? So therefore, c is log 2. Okay. So therefore, c is equals to log 2. So So we found C already. We need to substitute it back to the earlier expression. So therefore, log x is equal to here is equal to 80 plus log 4.2. Log 4.2. Sorry, log 4.2, right? Log 0.2. 4.2. Okay? Next time I suggest. Give it another 30 years, you say, same as me. Log of 0.2, so it's 0.2. So log x equals 80 plus log 0.2. Okay? So therefore, if you do your simple mathematics, just evaluate further, eventually you will get this. Log x over 0.2 is equals to 80, and therefore you have finally x equals to 0.2 times e to the power of 80, where e is Euler's constant, and e equals 2.718. Okay? So this is the expression for the x displacement of that particle. Now, we just look at x just now, we have to look at y. So now, take y component. Now, you will take y component. Or the velocity. Okay? So, v is equal to dy dt. So, in a similar manner, we have v is equal to dy dt. Right? And then, just as before, v is minus ay. V is equal to minus ay. Okay, from the first part of this solution. So it's equal to dy dt. Okay? So likewise, dy over y equals minus a dt. Right? Then, because again we want to obtain a relation between y and t. That's what we've done for x and t above here. Right? So then you integrate. Okay? So you will have log y, left hand side equals minus at, and plus a constant of integration. We must use e now, because we use c already. So again, we need to find the constant of integration e. We know that at time t equals 0, where's our y? I forgot to ask you to do a correction. Y is 0.2 and 80, not 0.8. 0.1. Let me make a correction here, the typo error. This is 80, Oh. Not 0.8. 80. Okay? This is because I have to use the same slide from Glasgow. This is not my typing, this is Glasgow professor's typing. And I noticed that actually it should be 0.8. So I told him it's not 0.8, it's 80. Okay, right. Y is equal to 80. Okay, at time t equals 0, y is equal to 80. So, So in this case, it would be the lowest streamline already. It is somewhere up. Okay, the streamline is somewhere up, not the lowest already. Because y is not 0.8 now, y is actually 80. So somewhere at the top, the streamline. Okay, so in this case, you have log 80, that's log y, is equals to, again, at time t equals 0, left hand side is 0, and plus d. So therefore, d is equals to log 80. Okay, so it's a substitute. D is log 80 back into the equation at the top. You get log y minus log 80 is equals to minus 80. Okay? Then, in a similar manner as before, eventually you will get y is equals to 80 e to the power minus 80. Okay? In other words, relationship between this fluid particle and time is that at time t equals to any value, the location of this particle is defined by this x and this y. This x and this y. Okay? So, in this case here, the half-line relation, so therefore, the half-line relation in this case is position xy is given by this 0.2 e to the power of 80. This with respect to time. X will vary in this manner with respect to time t, and y will vary in this manner with respect to time t. Okay, that's the half-line relation. So now we got this already. We are ready to answer the question: where is the new position of this particle at time t is equal to 6 seconds? So therefore, at time t is equal to 6 seconds, we nearly substitute t is equal to 6 into this relation, and we'll be able to find the new xy location of this particle at time t is equal to 6. So at t is equal to 6 seconds, the position or the location of the particle is xy, and this is equals to 0.2 e to the power of, what is a? A is 0.3, given as 0.3, and our t is 6. Okay? And the y position is 80, e to the power minus 0.3 times 6. Okay, close the bracket. So you get 1.2 and 13. Okay? So that's the new position of that particle at time t is equal to 6 seconds, where its x coordinate is 1.2, y is 13. Next, find the velocity magnitude and compare on whether the fluid particle accelerates or decelerates during its motion. Okay. So this fluid particle, we know its position at time t equals 6. But what is the magnitude of its velocity? What is the magnitude of its velocity? And having found the magnitude of velocity, can we tell whether it's accelerating or decelerating? Okay, so that is the question. Interesting question. So as you write, try to understand. So this is 4. Okay, what's the velocity magnitude? So what is in other words, you have to find what? Find the velocity magnitude. V is a vector. Okay? V is a vector. What's that? How do you actually denote the magnitude of a vector in applicable maths? Okay? Magnitude of a vector. To find the magnitude. Find V modulus. Okay, so how do we go about doing this? We have to make use of, we're still looking at the same particle. Okay. First, you can put in some numbers using the answers that we have found. So at time t equal to 0, okay, at time t equal to 0, we have u, the x component of the velocity, is equal to ax. This we know. What is a? A is given as 0.3. Okay? And what is x? X is 0.2. Okay? That's the initial position of the particle at time t equals 0. What is the vertical component of that velocity? It's minus ay. And a is 0.3 and y is at. So, okay, let's look at the top and the bottom there. This gives you 0.06 meter per second, and this one gives you minus 24 meters per second. Okay. So that's the situation at time t equals 0. Now what happened at time t equal to 6? So at t equal to 6 seconds. Okay. Similarly, what's our u now? U will be ax. A is 0.3. What's the x? X is now 1.2. Okay, we have found the answer already. So at time t equals 6, the x is 1.2. So this will give us 0.36 meters per second. Okay. So that's u. D, okay? D is minus ay, so it's minus a 0.3, and y is now the d. Okay? So this will work out to be minus 3.9 meters per second. Okay? So you see that, okay, so what's the magnitude in this case then? What's the magnitude? What's V modulus? So therefore, what is V modulus? Is equal to, anybody? Square root of u squared plus v squared. Okay? So if you do that, you should get 3.92 meters per second. Okay, if you do that. So at time t is equals to 0, at time t equals 0, okay, we know the magnitude at time t equal to 6. We have not calculated the magnitude at time t equals to 0. Because it was moving, but we start from, it was moving or it started at a point in time, we're still moving. So what's the v here? What's the v? At t equal to 0. Square root of u squared plus v squared. Okay? So this, u is so small, so effectively is almost still at 24 meters per second. Okay? So this is the magnitude at t equals 0. This is the magnitude at t equals to 6. So is it accelerating or decelerating? It is decelerating. gone slower already, from 24 meters per second to 3.92. So decelerating answer, huh? Decelerating. Okay, so we found the velocity magnitude at time t equal to 6. We know that it is decelerate. Huh? Decelerate. Okay, decelerate. Okay, and the last part, quickly we have a break, last part. Okay, 5. Show that the streamlines and half lines have the same profile. This they are the same. Okay? If the flow is considered to be steady. So if the flow is considered to be steady, okay, let's look at a half line. Let's set up a half line equation. We know half line is x to y is equal to something. So that's what's our x. Equation for the x is 0.2 e to the power of ad. Okay? Y is ad e to the power of minus ad. So these are our streamlines. Okay? These are our streamlines. And now, so if we multiply x and y, this gives us our half line. It has got no time involved. So xy is basically 0.2 e to the power of ad, a times ad, e to the power of minus ad. And if you work it out, it should be equal to 60. So remember x and y is equal to 60. This is half line. Half line. Okay. These are the streamlines. So streamlines, if you multiply them together, it gives you a half line. So therefore, they actually streamlines and half line, they have the same profile. Same profile. Right? So for half line, there's no time function. In this case here, our streamline function, and you put them together, gives you a half line x, y equals 60. So therefore, they are actually having the same profile. Okay? So we can say that they are same profile and they are actually yeah. So okay. Alright, so we just put that. Alright. Alright, if that any workshop time ready, we'll have a 5 minutes break.